Okay, one more problem, equilibrium calculation. Not really a calculation, it's just sort of a thought problem here. Let's look at this reaction. C diamond going to C graphite. Okay, it looks like this is a solid state reaction. Diamond going to graphite. All right, we say the equilibrium constant Kc is 3.22. Why is this statement wrong? Well, I don't know. Let's take a look. So what we're going to express, Kc, will be the concentration of, let's see, how do we write that? Graphite. So graphite concentration expressed in molar divided by concentration of diamond expressed in molar. But this is a solid and this is a solid. And remember what we said? Solids appear as just a unit. Pure solids appear just as a unit of 1 in equilibrium expressions. So this Kc, if you just press 1, is just 1. If you just put that in 1, is 1. And secondly, Kc implies that you have concentrations in molar. And here you have a solid, and what does it mean to have a solid and concentration in molar? I mean, molar is moles per liter of solution, and here's a solid. So it looks like whoever wrote this first part of the statement didn't know too much about equilibrium constants and so on. So statement is wrong. So there we go. It's not equilibrium. All right, let's look at the second part of the problem. One can calculate with thermodynamics that the equilibrium lies to the right in the above reaction, and we'll find out in a couple of chapters how actually to calculate that. So the equilibrium lies to the right, graphite. So why, for instance, if you have a diamond tie-tack or a diamond ring, why doesn't that turn to graphite? All diamonds eventually, because thermodynamically you say the equilibrium lies over here, so if you start with a diamond, it should go to graphite. Why doesn't diamond turn into graphite? Well, remember that there's a distinction between kinetics and equilibrium. So when you talk about equilibrium constant, we're talking about equilibrium. That's probably why they call it equilibrium constant. And equilibrium means you start with one thing and then you end up with something else and you run it to infinite time, and essentially it reaches equilibrium. So if we write, for instance, we'll be not really specific, but just call this an energy and call this a reaction coordinate. Equilibrium says, okay, there's the reactants and there's the products. In this case, this would be, the reactants will be diamond, and the products over here will be graphite. So that's all equilibrium says, where it starts and where it ends. Kinetics tells you how fast it goes from one place to another. So my guess is that for a diamond, the activation energy, is very, very large. Who knows how large it is, but it's very, very large. So even though thermodynamically, I mean, this is lower energy, and so we expect diamond to go to graphite, it takes so much activation energy to get from the reactant to the product that essentially it never happens. And why is that? Well, recall that diamond, the structure of diamond was you had carbons, and each carbon was bound to 4 other carbons in a 3-dimensional network. So you had carbons all bound together, really, really stable structure. They're all in the form of a tetrahedron. These carbons are sp3 hybridized, very stable. And so in order to go from diamond to graphite, graphite, recall, was you just have these planes of benzene rings and planes of benzene rings stacked on one top of one another. To go from the diamond to the graphite would require breaking these really stable bonds here and somehow making this. So even though graphite, yeah, all diamonds should turn to graphite, and if you wait an infinite length of time, which is a very long time, they will turn to graphite. But in fact, in our lifetime, and probably the lifetime of the universe, it will never actually happen. All right, that's it. Thanks.